This is the speed of the softball question. Part A asks, how fast is it going? What's its initial speed? When it's hit, it pops up at some angle theta. In my question, it flew for 2 seconds. There was a fielder who was already 18 meters away. That's about 20 yards away. The fielder saw the ball, ran, and 2 seconds later caught the ball in the outfield, somewhere here. So I do know that in 2 seconds, the ball has some kind of range, and it's caught. It's caught at the same level. That 2 seconds can give me important information, because that gives me the time that it takes the ball to rise and fall, and that's also the time that the ball has to cover some distance here. That's motion in the vertical direction, motion in the horizontal direction. That will allow me to calculate the vertical velocity and the horizontal velocity separately. I can then use Pythagoras to combine those two to figure out V0. So my first part, I cannot find this value straight away. The best I can do is find the vertical velocity and the horizontal velocity and combine them. Pythagoras would say a squared plus b squared is equal to c squared. For our triangle, we would translate that as vx squared plus vy squared is equal to v0 squared. These are all magnitudes, so you can then calculate v0. It would be the square root of the left side. So what is vx and what's vy? Quite simply, how fast are you going upwards if it takes 2 seconds to come back down? I think we could use, I think we're going to have to use y final equals y initial plus velocity initial in the y direction, delta t plus 1/2 a delta t squared for that. Our y final and y initial are the same, so this is going to be very, very similar to the planet X calculation. Our y final and y initial is the same level, it said. So whatever that is, they're going to be the same, so we can take those away. So if it was, say, 5 feet on both sides, minus 5 feet from both sides. Or we could just call that level here y equals 0, so that's 0. Either way, those two terms are gone. 0 is equal to the initial velocity in the y direction. The time, I know what the time is, but this is what I'm looking for. So let's see, that's known. My acceleration, this is acceleration due to gravity. They quote it to 2 decimal positions in this question, and it's downwards. So don't forget that it's going to be negative 9.81 meters per second squared. And we have a time, substitute that in. There's a delta t. So we know everything except Vy. Therefore, you can solve for Vy. The initial velocity in the y direction, you can solve for that. So that's some number. I'm going to assume we know it. Horizontal direction. Well, the fielder starts at 18 meters. When it's hit, 2 seconds later he catches it. That whole time he's cruising towards the outfield at 7 meters a second. So we can figure out how far he moves out from his starting position. That's a straightforward calculation. Constant velocity, we're going to assume. He just speeds up very quickly and runs. A simple kinematic equation, x final is equal to x initial plus velocity through time. That gives us change in position. He initially started out at 18 meters. We don't know where he ended up. That's what you want to know, this position here. This is his x final. And we know he went quickly. He went 7 meters per second in my case, and he had some time. He had 2 seconds in my case. So we can figure out x final from that. You can calculate that. So now you know this position, and so you know a total time, which is 2 seconds, and you know a total distance. This is how far that's how far the ball traveled in 2 seconds. So if we think about the ball now, not just the previous equation we were thinking about the outfielder, just to establish this final position. For the ball reaches that final position starting from an initial position of 0, right here at the origin, plus plus the initial velocity in the x direction. Actually, this is rubbish. There's no acceleration in the I can keep it. Plus delta t. We know the time. It's 2 seconds in my case. We don't know this initial horizontal velocity, but we do know this final position. We just calculated it. So we can now calculate the velocity in the horizontal direction that the ball was traveling. So presently we know the horizontal velocity, the vertical velocity. We can calculate the velocity of the ball by plugging both of these values into Pythagoras' theorem. That gives the hypotenuse, which is the original velocity.